thank you, everyone. Excuse me. Thank you, everyone. And it's really great to be with you this morning. And yes, I am aware that I'm standing between you and lunch. So I'll try to go ahead and just kind of jump into things. The earlier presentations from the speakers really did such a terrific job of I think, laying the foundation for my talk this morning. And really what I'd like to get at is more to the question of utilization, talking about biomass pretreatment and maybe where we need to be headed in looking at more efficient utilization of biomass for energy. At UT, we've been very fortunate over the course of the last 5 years through significant investment from then Governor Bredesen to allow us to really jump into the biofuels arena in a significant way. The UT Biofuels Initiative helped us develop really what I consider a pretty unique laboratory for study of not only fundamental work, but also very pragmatic challenges associated with the industry. You heard a little bit about the results of this Sunday, of this effort, as well as different times along the way. The piece at UT and the focus at UT has been really on the entire supply chain and trying to really advance that entire supply chain, given that there really are challenges at virtually every step of the way. We're fortunate in that we've got about 5,000 acres now of switchgrass under production, at least for the moment. The unique aspect here is that acreage is on any number of farms, so through contracting with individual farmers, that's allowed us to really refine management practices and gain considerable experience in the production and best management practices for this energy crop, and it remains an area of real focus for us. The other aspect of the infrastructure at UT includes now the Biomass Innovation Park. So the Biomass Innovation Park is essentially a pre-commercial pre-processing technology or pre-processing facility located in Von Orr, Tennessee, really enhancing our ability to study, again, movement of high tonnages of biomass. How do we efficiently handle, how do we store switchgrass and herbaceous or perennial crops while minimizing losses, and at the same time maintaining or even enhancing feedstock quality. The final piece of the loop here is in biorefining. So this was through a partnership with DuPont. At the time, DuPont Danisco, now DuPont Cellulosic Ethanol. There's a demonstration biorefinery on site in Von Orr, Tennessee, located right next to the Biomass Innovation Park. Capacity of about 250,000 gallons per year, targeting ethanol at this point. And also on site there, 100 scale PDU. So very unique, very rich capabilities for studying biochemical conversion of dedicated energy crops to liquid fuels. We've seen and heard, I believe it was Sunday, some of the outcomes, or one of the outcomes of this project with the commercial facility that DCE currently has under construction in Nevada, Iowa. You're welcome, Iowa. It's interesting now, and what I'd like to do is to talk a little more detail about this, the process, about the biochemical platform. And we've heard a little bit about this over the last couple of days, or yesterday and this morning. And as we look at the process, there really is a key step, and one that clearly distinguishes what we call advanced cellulosic biofuels from corn ethanol or conventional biofuels. And in this case, it's step 2, which is the pretreatment technology. So as we've heard, the challenge in advancing cellulosic biofuels and production of cellulosic biofuels really is in producing or generating access to the sugars in the cell wall. This requires a pretreatment step to really open up, or literally open up the cell wall structure and enabling access of enzymes to the carbohydrate component there. A number of technologies now are available. Includes things like dilute acid, steam explosion, or AFEX. In the case of DCE, I believe they're using actually a liquid ammonia process, but all designed to simply disrupt the cell wall structure and improve accessibility, again, to cellulose and the hemicelluloses. The interesting thing about this process, and really I think almost all of the what I might call first generation biorefineries that are emerging or being developed in the market, is that there's no focus on separations. So in this case, and all of the cases that I'm aware of at least, biomass comes into the front end of the plate or of the plant and is chemically pretreated to improve accessibility, but that entire biomass stream moves all the way through the process. So at the end of the process, there's ethanol product or butanol or other fuel product, and then really what amounts to a very complex residue that includes a number of other chemical components of the biomass, as well as the chemicals used in pretreatment, as well as enzymes, as well as or proteins, and as well as cell mass. So very complicated mix. Now, if you're focused strictly on fuels, and the only target is making fuels, this absolutely is the route to go. Again, a very low profit margin target. It's all about moving through that process. And I should also add that, of course, the residue at the end of the process is also, has some value for heat and power, some heat and power for the process, as well as power to the grid. But it's a very minimal, or at least what I consider to be a very minimal value associated with it. The other frustration that I share in looking at that approach is simply has to do with efficiencies and efficient use. And maybe to take just a minute to walk through this. And if we start out with a bale of switchgrass, maybe 1,000 pounds lying in the field, as we start to move that in or move that to the refinery, we know that we're moving about 20% moisture or 20% water along with it. So right off the bat, in terms of things that are, in terms of the product that we're interested in, we're losing 20% of the weight, which is in water. Switchgrass, the extractives level is about 10%, so extractives also not going to that fuel product that we're interested in. So we remove 10% of material there. Switchgrass, again, about 20% lignin content, not going to that ethanol fuel product. We pull that out to just expose the sugars. Then there's also, we're not perfect in our conversion and think maybe we're obtaining or getting to 85% of the sugars. So we pull out another 15%. The reality is, at the end of the day, we've invested a lot of money of moving material around, and we're not even using half of it. So it's a very inefficient process at this point in terms of utilizing the carbon. And oh, by the way, as we take a glucose molecule and convert it to ethanol, we're only going to use 4 of those carbon atoms as well. So they knock off another 30% off of this as well. So something that it's really important for us to consider in moving forward, and as we think about the next generation refineries, is how do we get more efficient at utilizing the carbon in this biomass? And we believe, at least, that really has important implications in the overall economic effectiveness and the logistics associated with biorefining. The implications are serious. You can see, and the good news is we've got some of our best engineers working on this as we're trying to move some pretty big loads of biomass around. But seriously, as we go down the road, the ripple effect and thinking about the volume of material that's required to to keep a plant running. There's some very real challenges from the field and logistics of delivering biomass to a refinery that are impacted by this efficiencies issue. Actually, we're doing a lot better than this these days. So we see a slightly different approach, and at least advocate for a slightly different approach as we start to move forward. And that approach really is what we call biomass fractionation. And I think probably by the time I get to the end of this, some of you will be tempted to call it biomass pulping or wood pulping. It's very much or very similar, I think, in concept to today's pulp and paper industry. But it's an approach that really is talking about rather than move the entire biomass through the stream, all of that material that is not going to provide us a fuel product, and end up with something very complicated at the back end that goes to a relatively low value use, to begin to evaluate and look very seriously at the prospect of separating the individual components of biomass at the front end. So in our case, we've been very interested and worked extensively in developing what we call the biomass fractionation reactor, or the solvent fractionation process. And you can see from this, well, I can tell you it's not as interesting as the missile from Vanderbilt. It's not much more than a stainless steel tube that the biomass is packed into. We have a fairly unique, I think, pulping liquor. It's made up of methyl isobutyl ketone, ethanol, water, and a little bit of sulfuric catalyst. But then that's pumped over the biomass, and at the end of the day, we collect a black liquor. Actually, at the end of about an hour and a half, we collect a black liquor, as well as then a solid cellulose residue. So it's a very convenient process for separating the individual components. Now, the reason for this liquor, and I should say this is essentially an organosolve process, one that's not so different from that being used by Lignol, and others have certainly explored over the years. But the interest for us is with this pulping liquor. So with that mixture of MIBK, ethanol, water, we have a single-phase system. And you can see from the ternary diagram that we're able to really design that pulping liquor and still maintain a single phase throughout or over very wide composition ranges. So that gives us quite a bit of flexibility in designing the pulping liquor for very specific chemistries to occur, and to really begin to design the pulping liquor for the variation in different biomass sources that are available to us. So the appeal here is that we start out with a single-phase solvent system, collect our black liquor, and this is typically run at about 140 degrees C, or somewhere between 120 and 160 being kind of the extremes. But we end up with a black liquor that contains lignin and also hemicellulose. The convenient aspect here is that by simply pouring water or adding water into the liquor, we're able to induce phase separation, and that phase separation then gives us individual streams of the components. So a very interesting process, and again, very convenient and simplified separations. This just gives you an indication of the result. Let's see if I can find the laser here. Yep. First of all, this is the cellulose product, or the cellulose fiber product. And here, we typically wash that product simply to get rid of residual liquor. And yes, you'll notice the high-tech toilet plunger there that's helping us keep water levels right. But then here's our black liquor mixture, and then after adding moisture to it, you see two distinct phases form. This organic phase in the top is rich in lignin, or essentially all lignin, and the aqueous phase that forms here in the bottom layer is a more complex mixture, contains some residual or water-soluble lignin components. It also contains fatty acids and other water-soluble pieces from wood. But again, two very clear and distinct process streams that enable additional work for us. So with that streams, what are the advantages of that? Now again, we're driven by the 800-pound gorilla of looking at fuels and production of fuels. And now the nice thing here, as we look at hydrolyzability or hydrolysis rates for the cellulose component, so that solid cellulose fiber that is left in the bottom of the reactor, given that we've removed the lignin, given that we've removed other inhibitors, we see an extremely high rate of conversion. So really reaching 80% and in about 2 days, 2 days' time. Typically, that's a 3 to 5 day hydrolysis process for most of the pretreatment technologies that are out there. Of course, the other appeal is that in fact this is still cellulose. So we have this what we would characterize as activated cellulose, and that activated cellulose has certain value or potential value as cellulose esters or other types of polymer materials. The other interesting and really important point as we think about logistics is that cellulose is very stable. So in terms of a breakdown or chemical rearrangements, not an issue. So storage is greatly improved if we're looking at year-round energy production or fuels production. So lots of advantages with that particular cellulose component in the production of either fuels or other high-value products. The piece that we've been particularly interested in is lignin. We heard about some of the lignin work earlier in the morning. Maybe just to share with you, I think many of you have heard the saying that you can make anything out of lignin but money. And and the truth is that's not really true. There are a number of companies making a lot of money, but as you look at this model structure, this model lignin structure, you can see where it might be a challenge. It's an extremely complex molecule and presents any number of barriers to really convenient utilization. There's been a lot of work targeting the use of lignin as a source of industrial chemicals, whether it's acids or other points, other types of products like that. Also as polymeric prepolymers or oligomers in phenolic resins, in phenol formaldehyde, or in polyurethane resin systems and the like. But the diversity of functionality and the complexity that this molecule presents continues to be a challenge in terms of really efficient utilization. The reality is, though, that we're faced with a new day. It really is a bright new horizon for lignin. And I started working on lignin 26 years ago in my master's work, and it's kind of like that bad dream that you just can't outrun. It's back, but it's back really in a much brighter point. For a number of reasons. Number one, we've got a number of new biomass sources available, or at least appearing on the landscape. So lots of flexibility and variability there. We've got new technologies. We're not really constrained or simply focused on craft process lignins. So there's new potential in terms of the chemistry and targeting the chemistry of lignin for downstream uses. To me, the real level of excitement comes from the talk that you heard from an earlier speaker, and that has to do with the remarkable progress that molecular geneticists and the genomics world have made in being able to really control the biosynthetic pathway of lignin and begin to really design, even in the plant cell wall, the structure of this material. And that has some very real implications in terms of what we might do with it downstream. So just very briefly looking at this lignin structure, again, being able to manipulate the individual monomer components or the volumes of monomer components, syringyl guaiacol, coumarate, are particularly important to utilization potential, mainly because they influence the number of beta-O4 linkages, or this rather classic ether linkage that occurs in lignin. It's one that really dominates the properties of lignin for any number of applications. The excitement to me comes too in marrying together the new pretreatment or fractionation technologies with the chemistries that are available from biomass lignins these days as well. With the clean fractionation reactor, we're able to really very finely fine-tune the amount of beta-O4 linkages. It really target the beta-O4 linkages that are generated in the lignin preparations that we isolate. So depending on the biomass source, depending on the reaction conditions, that liquor formulation, we have a number of points of control for that particular structural feature. Now, the reason that particular structural feature is important to us is really we're interested still in the polymer properties of lignin. And in being able to manipulate and control the polymer properties, things such as the glass transition temperature is something that really is very important for downstream applications. Again, just to give you a little bit of an indication here, this is a raw lignin. From the organosolve process, from the clean fractionation reactor. And the glass transition here is hovering around 145 degrees Celsius. We're able then to actually go and upgrade as a based on different solubilities and generate a number of fractions of lignin with glass transitions ranging all the way from maybe 80 degrees at the low end up to about 180, 190 degrees. So an extremely wide range of glass transition. Now you're familiar with glass transition. It's the temperature where the material goes from a solid or a resin to a melt or a rubbery state. So it's very important in processing. And the reason we're interested in melt flow has to do with the prospect of utilizing lignin as a precursor for carbon fiber. This is potentially a real game changer as we talk about a relatively low-cost precursor for the production of this very high value, very high volume material system. And so we're excited to see some real progress being made there. Although I will freely admit we're a long way from automotive and even further away from space shuttle or 757 applications, but we're making genuine progress as a consequence of being able to understand more directly the relationship between chemistry, between processing, or chemistry of the lignin processing behavior and the performance of the product. The image here just shows you some green lignin. So this is a lignin that has been spun into a fiber. Close-up of or scanning electron micrographs of carbonized lignin fiber now. So this is a lignin carbon fiber that's been produced. You can see a very uniform fiber, very smooth surface, free of defects, and all of this really very exciting progress in terms of being able to produce this kind of high-value material. I have to tell you, I was driving home Friday night and I heard an interview on NPR, so I'm assuming I can share this quote with you. But the president of a carbon fiber company was being interviewed, and he pointed out that making carbon fiber is a lot like sex. You can read about it, you can talk about it, but until you've done it, you don't really know what it's like. And I can tell you there are some real challenges in making carbon fiber, and even greater challenges in making carbon fiber from lignin. But that capacity to design and to tailor The properties of that lignin precursor are critical. If the TG is too high, we cannot spin the fiber. If the TG is too low, stabilization time of the fiber goes to days, and again, in a commercial process, unacceptable. So real challenges there. There's also some very interesting options. If you think about that very high TG lignin fraction that I showed earlier, that material won't melt flow. So we've looked instead at electrospinning, since it is still a soluble lignin. And you can see that we're able to electrospin nanoscale fibers and less than 100 nanometers in width, very uniform and continuously. The exciting thing here, with that high TG, we're able to stabilize this fiber, actually cut it down from days to 1 hour. So 1 hour stabilization gets us to some very exciting commercial potential. Just a few remarks to conclude. You know, the first generation refineries being solely focused on fuels just leads to such a tremendous inefficiency in carbon use that we believe really it's imperative for us in looking at economic feasibility and improving margins, as well as simply improving the utilization of this natural resource, that it's imperative we begin to look at these types of front-end fractionation scenarios where we can produce individual process streams for upgrading in downstream technologies. Incredibly exciting with the expanded biomass sources, with the new capacities that are being developed in molecular genetics. The potential for utilizing this historically or traditionally underutilized component of lignocellulosic materials is really exciting, and we're looking forward to continue to develop this particular component. And just a quick thank you to my compadres, Joe Bozell, Nicola Bay, Darren Baker, and also to the sponsors that have supported this work. And to you for your attention. Thank you.
So I'm sure Tim would be happy to answer any questions you might have.
Tim, very nice. Have you done a study of the change in the cost of the processing if you move from a consolidated process to this front-end fractionation and then conversion?
No, is the short answer. And you know, the reality is, and I would emphasize, you know, if you're looking at fuels or a commodity product only, this simply is not an option, because obviously it's an expensive front-end pretreatment there. But as we begin to look at value-added chemicals and kind of the role of value-added chemicals from carbohydrates, from lignin, we're optimistic, at least, that the economics here are favorable. It's something that desperately needs to be done, though.
We have a question over here in the center.
Yes, I was wondering what happened to the hemicellulose and the hemicellulose sugar in your fractionation. We had the lignin at the top.
Yes. Oh, hi. Sorry. Yes. So again, we have not focused a lot of work on the aqueous phase mixture, but the Hemis. Our intent is essentially the Hemis get added back onto the cellulosic sheet and carried through for fermentation, or hydrolysis and fermentation. Although I have to say we've been surprised there are companies out there that are very interested in C5 sugars as a foundation for industrial chemicals.
Thank you.
Any other questions out there? Tim, would you care to address what the efficiency in the current system that you're utilizing? What's the current efficiency of recovery for your solvents?
Jeff. Well, you know, we are in a laboratory environment at the moment. And actually in the lab, it's pretty high. Certainly, the solvent issue is something that we're aware of. I can't say that we've considered it a great deal at this point. We are optimistic, though, that frankly with some new membrane technology that is out there, and also beginning to look at industrial practices like spray drying as opposed to rotovapping or some of these other kinds of really industrial chem applications, that we're able to handle this. We know that this process has been considered extensively over the years by a number of groups, and generally favorably reviewed. So we just really are at a point where the driver is value-added products and ideally value-added products coming from that lignin component.
Great. Well, why don't you join me in thanking Tim as well as all the rest of our speakers for this session.